Dear colleagues, this is Guangyao from Ocean University of China. Here I would like to present you the intercomparisons of Aeolus and a ground-based coherent Doppler Lidars network over China and their science applications. So this is the outlines of this topic, and including the motivation, the carve-out of the Aeolus with ground-based coherent Doppler Lidar, and also its science application of dust transport and advection measurement with the spaceborne lidars and model data. And finally, I will give you the conclusion. So, as known to all, there are several dynamic systems all over the world. For instance, in tropics, the large-scale motion systems and El Nino phenomena need to be investigated further. And in extratropics, the continuously jet stream measurements are essential for the planning of long-distance commercial flights, and it affects both cloud formation and radioactive energy transfer. Also, the wind field is particularly needed in the areas of the rapid changing, such as in storm systems, in large-scale weather system research. It can also provide us more information in understanding the pollution transportation. Hence, large-scale change event has a decisive impact on the weather patterns and the long-term evolutions of the Earth's climate. So, in the numerical weather prediction, there are some methods in determining the wind informations, including the radio sound network, aircraft data, satellite soundings, and atmospheric motion vectors. However, wind profiles information measured with radio sound is generally lacking over all ocean areas. And for the aircraft data, they are only available around the 10 kilometers level. Even at airports, the vertical profiles are also transmitted. And as for the satellite sounding, it provides temperature and humidity soundings from the polar orbiting satellite, and which is also available at ECMWF. But the temperature and humidity profiles information from satellite provides reasonably uniform coverage. And as for the atmospheric motion vectors, which is also available from ECMWF, but the main data source is cloud track wind over tropical regions as observed from stationary satellites. Over polar regions, the water vapor channels on polar orbiting satellites are also used to track winds. To be concluded, after this short review, currently, the global observation system used for the NWP has some limitations in data coverage, measurement height, continuously of detection, and data accuracies. So, before the launch of the Aeolus, the wind profiles at all levels outside the main populated areas, particularly in the tropicals and in the stratospheres, is the most critical atmospheric variables that are not adequately measured by current or planned systems. There are about 90 satellite data products, and beyond 60% observations are measured with the satellite. Only 0.1% is from radio sound. In North Hemisphere extratropics, radio sound plays main roles in observation. In South Hemisphere extratropics, satellites radiance plays this role. After assessment of the Aeolus data, it is found Aeolus contributes 0.3% fractions in the numerical weather prediction. According to the forecast diagnostics from the Dota and Liu, it is found that normally the Aeolus wind data perform better than models did. So, on 22nd August 2018, Aeolus was successfully launched into its Sun synchronous orbit at height of 320 kilometers. And the quasi-global coverage is achieved daily. For example, 15 orbits per day, and the orbit repeat cycle is 7 days. And during this cycle or this duration, there's 111 orbits we got. And the orbit is synchronous with a local equatorial crossing times of about 6 a.m. and p.m. And Aladdin is the unique payload of the Aeolus. It is a direct detection high spectral resolution wind lidar. It works at the wavelength of 355 nanometers with a laser pulse energy around 65 million joules and with a repetition of around 50 Hz. As the receiver, a 1.5 meters diameter telescope collects the backscattered light. In order to retrieve the lost wind spans, the Doppler shifts of light caused by the motion of the models and the aerosol particles need to be identified. Aiming at this, a piezo interferometer is applied in the mid-channels to extract the frequency shift of the narrow band and the particulate return signal by means of the fridge image techniques. And in the relay channels, two coupled Fabry-Perot interferometers are used to analyze the frequency shift of the broadband molecular return signals by the double-edged techniques. And the two channels high spectral resolution design with Aladdin allows for the simultaneous detection of the molecular and the particle backscattered signal. It supports the wind in 24 vertical high spins with a vertical range resolution between 0.5 kilometers and 2 kilometers. And this makes it possible to deliver winds both in clear and partly cloud conditions down to the optical thin cloud at the same time. The horizontal resolution of the wind observation is about 90 kilometers for the relay channels and about 10 kilometers for the mid channel. And after the successful launch of the Aladdin, the data products have been released to the Aeolus Guangyao teams on 16th December 2018. To recheck the quality of the data products, a validation of Aeolus wise by means of the ground-based airborne shipborne reference instrument measured are inevitable. And the quality assessment of the satellite data products is based on the verifications observation results on multiple platforms and devices. And comprehensive analysis of the results can provide important analysis support for further improvement of satellite performance, inversion algorithms, and the quality control. And about half an hour after the launch of the Aeolus, the validation campaign, we named it the WOW OUC, performed by the Ocean University of China, have been carried out since the January of 2020 at 17 stations, and the durations of the validation campaigns was from January to December 2020. And the location of the coherent Doppler lidars, the ascending and descending orbits of Aeolus are shown in the left figures. And also in the right tables, we also provide the more information about the coherent Doppler wind lidar. So in the WOW OUC campaign, we use a coherent Doppler lidar as the reference instrument. And the 550 nanometers wavelengths of 5 coherent Doppler wind lidars with high resolution takes advantage of the fact that the frequency of the echo signal is shifted from the local oscillator, right, because of the Doppler shift which occurs from the backscattering of aerosols. And the Doppler frequency shift of the backscattered signal is analyzed to obtain the loss velocities along the lidar beam direction. The coherent Doppler wind lidar is based on the hydrodyne techniques. consisting of a signal frequency set laser source, AOM, and amplifier, optical insulators, and the amplified emission noisy filters, and the optical switch, a transceiver telescope, balanced detector, and an analog to digital converter, and a fast Fourier transform signal processor. The coherent Doppler lidar of types WIND 3D 6000 and WindMaster PBL are light systems for wind measurement in the lower atmosphere. The device was developed by the laser transit technology and designed with considerations for the needs for the meteorological application, wind energy industry, and aviation safety. And in this study, we use this WindMaster PBL and Wind 3D 6000. And here I provide the specifications of the coherent Doppler lidars. The left table summarized the specifications of Wind 3D 6000. It is found that the detection range covers from 80 meters to 6 kilometers. And the right table showed the specifications of the WindMaster PBL. Its detection range is slightly lower than the type of Wind 3D 6000 did. It covers from 30 meters to 4 kilometers. And to evaluate the accuracy of the ground-based coherent Doppler lidar measurement, the Wind 3D 6000 and the WindMaster PBL was validated with the mast-mounted anemometers and wind vanes at the Haiyang, Shandong province of China. The photos of the coherent Doppler wind lidars and the master that are mounted here, and the wind vanes at site Haiyang are also shown in the middle in the left fingers, and the comparison results of the wind speed and wind directions for these two lidars are shown respectively. By performing the ordinary least square linear regression of the coherent Doppler wind lidar and the CAP and anemometers and wind vanes while measurement, the slopes, offsets, the standard deviations, and correlation coefficients are acquired, and they are within the acceptable limits. The statistical analysis of the validation are shown in the right table. Hence, the coherent Doppler wind lidar of type Wind 3D 6000 and the WindMaster PBL can be act as the reference instrument for the validation of Aeolus in the atmospheric boundary layer. And in this slide, we provide the flowchart of the comparison between the coherent Doppler wind lidar measurement against the Aeolus measurement. To ensure the quality of the measurement data from Wind 3D 6000 and WindMaster PBL, we only use the coherent Doppler wind lidar with the signal-to-noise ratio is larger than -10 dB. For Aeolus, only observation with the corresponding validate flag of true are considered. Now for the comparison, only the mid-cloudy and the really clear wind velocities from the L2B products with estimated errors lower than 4 meters per second and 8 meters per second respectively are selected for the comparison. Moreover, the Aeolus the lowest atmospheric beings close to the ground are always removed from the comparison because the lowest atmospheric rich beings from Aeolus could be contaminated with ground. In this study, the horizontal separation between the location of the coherent Doppler wind lidars and the Aeolus measurement ground-based ground tracked should be less than 80 kilometers, since the coherent Doppler wind lidar provides continuously atmospheric observation, so theoretically there is no time difference between coherent Doppler wind lidar and simultaneously Aeolus measurement. And I also would like to see the vertical average of the coherent Doppler wind lidar produced wind measurements over Aeolus range beams is performed. In the atmospheric boundary layer, the vertical velocity of air mass shows pronounced impact on the horizontal line of sight when the velocity is measured by the Aeolus. The schematic diagram of the vertical velocity impact on the horizontal light of sight velocity retrieved is presented. Hence, the difference between the H loss when the velocities from coherent Doppler lidars and Aeolus should be specially treated for the comparison. As shown in the upper figures, the off-nadir angle of the Aladdin is 35 degrees, but because of the curvature of the Earth's surface, the viewing angle of the laser beam from ground becomes 37 degrees, which is used in the vertical velocity correction. Above all, the relationship between the Aeolus retrieved H loss and the coherent Doppler lidar produced H loss should be calculated with the equation 2. And to compare the measurement results in Qingdao, the simultaneous profile of H loss when the velocity is observed with Aeolus and when 3D 6000 are provided in the left figures. From this figure, it is found that the Aeolus level 2b really clear H loss profiles in the atmospheric boundary layer are almost trustable, except for the lowest height beams of the Aeolus really clear H loss profile, which has a large bias comparing with the coherent Doppler lidar retrieved H loss wind. In this aspect of the Aeolus level 2b mi-cloudy H loss profile in the atmospheric boundary layer, the synchronous coherent Doppler lidar measurements are in the range of the Aeolus estimated error. And we also provide the full simultaneous profile of the H loss when the velocity is observed with Aeolus and the coherent Doppler lidar on 21st January, 11th April, 18th September and 15th November 2020. It is also found they are fitted well. And in this slide, we compare the H loss when the velocity results from the Aeolus observations with the accompanying ground-based coherent Doppler lidar measurements. During the time period of January to December 2020 with the one OUC campaign, and 52 simultaneous mi-cloudy comparison pairs and 387 really clear comparison pairs at 17 stations are acquired. This figure below this figure below shows the numbers of the comparison data pairs as different detection height ranges of mi-cloudy channels and really clear channels. It can be seen that the heights of the comparison pairs are mainly in and close to the atmospheric boundary layer. In this slide, the mi-cloudy H loss when the velocities and the really clear H loss when the velocities from Aeolus and comparisons with that from coherent Doppler lidar respectively. It should be emphasized that before this comparisons process, the outliers controller is conducted firstly. The data with H loss difference larger than 1 standard deviations are removed and are not considered for the comparison. And for mi-cloudy H loss when and really clear H loss when 15 comparison pairs and 94 comparison pairs are removed respectively. And the table summarized the statistical results of the comparison. And we can find the correlation coefficients, the standard deviation, the skewed mean absolute deviation, and the bias from the mi-cloudy and the really clear H loss channels are compared and presented here. And additionally, the scatter plots and the statistical histograms of the Aeolus really clear H loss against the coherent Doppler lidar retrieved H loss according to the measurement made on ascending and descending tracks are presented individually. It is found that the standard deviation and the bias on ascending tracks are slightly better than that on descending tracks. And to evaluate the impact of updating baseline products on the H-loss measurements, the Aeolus level 2B really clear H-loss data from baseline 7 and baseline 8, baseline 9, baseline 10, and baseline 11 are compared against the coherent Doppler Lidar retrieved individually. During the comparison period, the Aeolus level 2B H-loss measurement between January and April 2020 are produced with the baseline 7 and baseline 8, and the measurement between May and September 2020 and with the baseline 9 and baseline 10, and the rest measurement from October 2020 are supported by baseline 11. So, after the mirror's temperature bias correction, processor was deployed and the new relay channel threshold were added. The performance of Aeolus wind measurement and baseline 9, baseline 10, baseline 11 were improved significantly than that from baseline 7 and 8. And in these slides, we've summarized the recent comparisons campaigns from the Guangyao teams all over the world, and the corresponding campaigns results are presented. And the statistical parameters, including the correlation coefficient, standard deviation, mean absolute deviation, bias, slope, and the intercept of the recent calibration and validation campaigns shows the consistent tendency and similar comparisons results. And this is the result of the really clear channels. And this slide shows the results for the mid-cloudy channels. So you can also find the reference on the website. And so then we switch to the science applications of the Aeolus data. We name it the dust transport and advection measured with the spaceborne lidars and model data. And in this study, we use Aeolus and the Cleop measurement data, and the tables provide the specifications of them. And for the identifications of dust and the mass concentration calculation, the level 2C wind vector and extinction coefficient at 355 nanometers from Aeolus, the extinction and backscatter coefficient and the depolarization ratios from Calypso are used. And the ECMWF provides the atmospheric reanalysis ERA5, which presents a detailed record of the global atmosphere, land surface, and ocean waves from 1950s onwards. And the 4D world assimilated ERA5 products are hourly vertical profiles, global wind field with a grid resolution of 31 kilometers. And the high-speed is a modeling system for determining the trajectory, transport, and dispersion of air masses. And backward and forward trajectories are the most commonly used models applications to determine the origin of the air mass. In this study, high speed is used to describe and check the routines of the transport, dispersion, and depositions of dust plumes. In the left fingers, to identify the dust event and to choose the closely synchronized observation with Aladdin and Cleop, the dust score index data provided by Aqua are used to determine the dust plumes coverage and the transport routine. With this information, the vertical feature mask products from the simultaneous observation with Cleop are applied to cross-check the identification of dust events. Hence, the vertical distribution of dust plumes are obtained, and to find the original source and to predict the transport routine of the dust plume, the backward trajectory and the forward trajectory are used respectively. And when the dust events are determined, the simultaneous observation with Aladdin and the Cleop have to be selected. Starting from the Cleop observations, the nearest Aeolus footprint were found, and since the orbit of the Aeolus and Calypso are different, they cannot meet each other at the exactly same time and same location. And from our study, the closest Calypso scanning tracks to those of Aeolus are about 4 hours ahead of Aeolus. Based on the transport directions and dust event modeling with high split, the tracks of Aeolus should always be downwind of the tracks of Calypso. And when the tracks of the Aeolus and Calypso are selected, the distance between the tracks can be calculated. As we assume the wind speed between the Calypso scanning tracks and the Aeolus is in the range of 5 to 15 meters per second, the transport distance of the dust plume are in the range of the 72 kilometers and 200 and around 200 kilometers. And during this short period, dust optical properties remained almost unchanged. And consequently, as the distance between the two satellite scanning tracks are less than 2 kilometers and the tracks of the Aeolus are downwind of the tracks of the Calypso, it is reasonable to be stated that the dust plumes captured by the Calypso are transported towards to the Aeolus scanning regions in around 4 hours. And hence the following producers can be continued. And to be concluded, a successful match at least meets two criterions, including the first one, the tracks of the Aeolus are downwind of the tracks of Calypso, and the second one, the distance between the two satellites scanning tracks are less than 200 kilometers. And in the right figures, the flowchart of the dust mass concentration, the dust mass advection calculation procedures is provided. Based on the dataset consisting the backscatter coefficient and extinction coefficient at the wavelengths of 1064 nanometers and 532 nanometers from Calliope, and the extinction coefficient at the wavelengths of 355 nanometers from Aladdin, the aerosol volume concentration distributions can be estimated based on the regularization methods which was performed by the generalized cross-validation. From Mueller, the LiDAR ratios for the Western Sahara dust is higher than the global average taken for the Calypso retrieval. And thus the extinction from the Calypso level 2 products are not used in this calculation of the aerosol volume concentration. And the extinction at 532 nanometers and 1064 nanometers utilized for the regularization method and are calculated from the Calypso backscatter, and the corrected LiDAR ratios are used in this study. So, in the left figures, the dust score index provided by the aqua at different stages are presented. And from this figure, the long-term dust event generated on 14th and 15th June 2020 from the Saharan Desert in the North Africa, this spread and moved westwards over the Atlantic Ocean, and finally being deposited in the western part of the Atlantic Ocean, the Americas, and the Caribbean seas. It also should be emphasized that since the dust scores are improved per day, the dust events are just preliminary classified. And from the space-bound Calypso Calliope measurement, it is found that sometimes dust events are actually presented but are misjudged by aqua, which may result from the interference of the high-altitude cloud layer. And the daily dust scores data over the Sahara, Atlantic, Americas regions generally rewards the transportation of the dust plume horizontally. And to cross-check the transport routing of dust event, 3 adjust typical aerosol profiles capturing dust aerosol layers from one Calypso orbit, and the corresponding backward and forward trajectories are starting at 4 a.m. UTC 19th June 2020 of these 3 positions conducted with the NOAA high-split models are shown in the right figure. And in this section, the dust event observation snapshot captured by Aladdin and Cleop on 19th June 2020 is introduced in detail, and the course's synchronized observation from Aladdin and Cleop on 19th June 2020 are presented in the left figure, where the purple lines indicate the scanning tracks of Aladdin and the green lines indicate the scanning tracks of Calypso. It is found that the overpass of each satellite are only around 3 hours apart. Hence, we captured the dust layers on the morning of 19th June 2020, courses simultaneously over the Western Sahara, the Middle Atlantic, and the Western Atlantic. For example, took a snapshot of the dust plume, and from the profiling of the dust optical properties discriminated by the Cleop measurement, the dust and geographical distribution over the Atlantic Ocean on these days could be determined, and the extinction coefficient and backscatter coefficient at the wavelengths of 355 nanometers, 532 nanometers, and 1064 nanometers within the dust mass are also determined. And on this day, the dust layers existed over the Western Sahara, the Middle Atlantic, and the Western Atlantic courses simultaneously, which indicates that the dust plumes areas over the Atlantic on the morning of this day is quite large, and this dust transport is massive and extensive. And to calculate the dust advection during this event, the wind field and the relative humidity informations are necessary. And since the observation with Aladdin and Cleop are not exactly simultaneously, and the stability of the wind field between the scanning tracks of them has to be estimated. Hence, the wind speed, wind direction, and the relative humidity between the tracks are analyzed with the data from ECMWF, as shown in the middle figures. It should be emphasized that during the computation of the dust advection, the results with the relative humidity higher than 90% has to be removed. So, during the dust event, the courses synchronized observation with Aladdin and Cleop were selected to follow the transport and the dispersion of dust. The detailed information about the Aladdin and the Cleop observation on 15th, 16th, 19th, 24th, 27th June 2020 along the transport routing and the high-split modeling are shown in the left figure. In this figure, the scanning tracks of the Aladdin and the Cleop on these days are indicated by dark purple lines and green lines, respectively. And the high-split trajectory models from the altitude of 3 kilometers, 4 kilometers, 5 kilometers at position A, B, C are shown respectively also in this figure. And the square symbols in this figure indicates the high-split trajectories possession corresponding to the 5 cross-sections in time dimensions. In this figure, the 5 cross-sections of the extinction coefficient at 355 nanometers measured at different times with Aeolus, and 5 cross-sections of backscatter coefficient at 532 nanometers measured at different times with Cleop are plotted respectively, and additionally, the forward trajectory and the backward trajectory and the presented in dark red lines and light purple lines in this figure. And from this figure, we can find that at the different cross sections of Aeolus and Calypso, the dust transport modeled with high split matched well, especially with the enhanced backscatter and extinction coefficient values indicate the presence of the dust. And the table presents the two sets of the mean mass concentration of each cross-sections at different times during the dust transport calculated by the retrieval method and the factor method. And compared with the factors measured calculation result, it is considered that the dust mass concentration from the retrieval method is reasonable and accessible. And here I have to do some explanation about the factor method, and this is given from the literature report, and we use this as the reference method, and we used our retrieval data to compare with the vector data. So we find that this is correct. So this is the overview for this dust advection measurement. So we used the dust optical properties. We plus the wind field provided by the Aeolus and the ECMWF, and then we got the dust advection and depositions. But if we think further, and we can also get the chlorophyll concentrations from the MODIS measurement, and we use the dust deposition data, and we can also find some fertilizations effect on the ocean. So this is the further research, and I will not say too much. So here I would like to give you the conclusion of these two studies. The first one is the framework of the Aeolus in 2020. The ground-based coherent Doppler Lidars are deployed at 17 observation stations over China for simultaneous measurement. And after the strict quality control, 52 simultaneous me-cloudy comparison pairs and 387 really clear comparison pairs from these campaigns are acquired. Now, using the simultaneous wind measurement with coherent Doppler Lidars and Aeolus, and the really clear H-loss wind velocities and the me-cloudy H-loss wind velocities from Aeolus are compared with that from the coherent Doppler Lidar respectively. And we also get the comparison for the me-cloudy and really clear. And it is found that the standard deviation and bias on the ascending tracks are slightly better than that on the descending tracks. And after the mirror temperature bias correction processor was deployed and the new radio channel stereo were added, resulting in the performance of the Aeolus wind measurement and the baseline 9, 10, 11 were improved significantly than that from the baseline 7 and the baseline 8. So we can still see some misfit. This is maybe result from the contaminations of the me backscatter signal to really backscatter signal, which introduced errors to the retrieval of really clear H-loss velocity. It is figured out that these figures acquired similar results compared with other recent in comparison campaigns, and all the comparison results shows consistent tendency. And in the atmospheric boundary layer, the vertical velocity from the convection and the turbulence could influence the comparison. So all of this conclusion, you can get more information from this reference we listed below. And for the science application of the dust transport, we can also find some conclusion. The first one is a long-term, large-scale Sahara dust transport event that occurred in June 2020 is tracked, and its mass advection is calculated with the remote measurement data from Aladdin and Cleop, and also the analysis data from ECMWF and the high split. And we use this, and we also use this dust event to evaluate the performance of the Aladdin and the Cleop on the observation of the dust optical properties and the wind field, and to explore the capability of tracking and dust event and in the calculating the dust mass advection. And the second one, the emission, dispersion, transport, and the deposition of the dust event are followed using the data from high split, Cleop, and Aqua. With the closely synchronized observation from Aladdin and the Cleop, combined with the wind data, the wind field, and the relative humidity from the ECMWF, the dust advection is calculated. And from this study, it is found the dust event generated on 14th and 15th June 2020 from Saharan Desert in North Africa, and dispersed and moved westwards over the Atlantic Ocean, and finally being deposited in the west part of the Atlantic Ocean and the Americas and the Caribbean seas. And during the transport and deposition process, the dust plume was trapped and transported in the northwesterly trade wind zone between the latitude of 5 degrees and 30 degrees and the altitude of ground to 6 kilometers. And the Aeolus provides the observation of dynamics of the dust transport event in the Sahara air layer. And finally, the vector at different dust part and height on 19th June and on the entire transport routing during the transportation are calculated respectively. And in the whole lifetime of the dust event, the mean dust advection values are calculated. And during the dust development stage, the mean advection values gradually increased and reached the maximum values on 16th June with the enhancement of the dust event. Then the mass advection values decreased since most of the dust was deposited in the Atlantic Ocean, the Americas, and the Caribbean seas. And for more information, you can also find the reference listed below. So that's it. Thanks.